Okay, in part 3 of lecture 19, we are going to learn about the design techniques for a Butterworth filter. Right, and again, I wish to stress that our reference for this Butterworth filter is a low pass type. Yeah. Okay, so these are the steps that will be taken for the Butterworth filter design. Number 1, we have to calculate the filter order using equation number 5. Okay, bear in mind that the filter order must be an integer. For instance, if we get the value is 1.7, so we must round it up to 2. If we get the value of 1.2, also we need to round up to 2 as long as the value is bigger than 1. So we have to round up to 2, and also if the value is 3.45, we have to round up to 4 for examples. Yeah. So equation number 5, if you can recall back to which equations will be these equations here. Okay, these equations, we have 4 important informations to be substituted, which are the alpha S, the alpha P, the omega S, and omega P. So these 4 parameters shall be provided to you in order for you to design or in order for you to calculate the filter order N. So, yeah, so I repeat again, these 4 informations here, the cutoff, sorry, not the cutoff, the passband gain, alpha P, the stop band gain, alpha S, the stop band frequency, omega S, and the passband frequency, omega P. All of these 4 parameters must be given. Then only you can calculate the filter order N. Yeah. Okay, number 2, once you have the filter order N, you are going to calculate the value of the cutoff frequency using equation 6 and equation 7. Okay, and these cutoff frequencies will be used to calculate the passband gain alpha P and the stop band gain alpha S using equations 2 and equations 3 respectively. Okay, so these are the rule of thumbs that we need to follow in order to select the cutoff frequencies. Remember that from equation 6 and 7, we are supposed to have 2 different values of cutoff frequencies. Equation 6 is cutoff frequencies obtained from the passband information, the alpha P and omega P. Equation 7 is the cutoff frequency which is obtained from the stop band gain and stop band frequency. Okay, so we need to choose from these 2 equations, or from these 2 cutoff frequencies, we need to choose the cutoff frequencies which will give us the calculated alpha P must be bigger than the specification of alpha P, and the calculated alpha S must be smaller than the given specification of alpha S. So these are the rule of thumb that need to be followed in order for us to choose the cutoff frequencies. Yeah. Okay, so from 6 and 7, if you can recall back from the previous slide, okay, 6 and 7, we are supposed to get 2 cutoff frequencies. Yeah. Okay, so from these obtained cutoff frequencies, we have to substitute those cutoff frequencies to equations 2 and equations 3. Yeah, so we need to substitute both cutoff frequencies into equations 2 and equations 3, and we are supposed to get 2 sets of alpha P and 2 sets of alpha S. Am I right? Yeah, so we are supposed to get 2 values of alpha P and 2 values of alpha S. Okay, so we need to choose the cutoff frequencies that follow this rule of thumb. Calculated should be bigger than the specification. Calculated alpha S shall be smaller than specification of alpha S. Okay, I'm hoping that by the examples I'm going to show you after this, you're going to understand more on these steps too. Yeah. Okay, step number 3, once we have obtained the cutoff frequencies, we shall then proceed with obtaining the normalized transfer function, which is based on the filter order N, in which the normalized transfer function HNS shall be based on the Butterworth filter, yeah, in which HNS equals to 1 over B and S. B and S is the Butterworth polynomial. Okay, and the Butterworth polynomial will be depending on the filter order N. All right. And once you obtain a normalized transfer function, we are going to proceed with chapter 4, in which we are going to calculate the actual transfer function Hs of the filter by substituting or replacing S with S over omega C in a polynomial of H and S. Because we are dealing with the low pass filter, so the S terms in your normalized transfer function shall be then substituted by S over omega C, in which omega C is the one that we have chose from step 2 just now. Okay, if your filter is a high pass filter, so your transformation shall be omega C over S. And since we are using low pass filter, so the S terms in your normalized transfer function shall be substituted by S over omega C. If you are using a high pass filter, the S terms in your normalized transfer function shall be substituted by omega C divided by S. Yeah, so hopefully you understand this step number 4. Okay, so let's have a look at these examples. So these examples request us to determine the order of the Butterworth filter. So we are given the specifications here where we have omega P of 100, omega S of 200, alpha P of negative 0.5 dB, and alpha S of negative 20 dB. Okay, so by using equation number 5, we are going to substitute all of these 4 terms in these equations, and we are supposed to get a value of 4.8. So 4.8 is bigger than 4, so the actual value of n shall be equals to 5. So the filters with this specification, the filters order shall be equals to 5. Yeah. Okay. When calculating this n, please bear in mind that the substitution of alpha S and alpha P in these equations need to be a positive value. Means that you shall ignore the negative sign in alpha P and alpha S when calculating these numerical values of n. Okay, so please bear in mind about this case where we have to ignore the negative sign for the alpha P and the alpha S. Yeah. Okay, it's very simple examples, calculation of n. All right. Right. So this is the actual examples on the Butterworth response, where we need to design a Butterworth low pass filter with the following specification. We are given the pass band gain between 1 and 0.891. Okay, so this is not in dB. Okay, this is in linear scale. So we have to change into a dB value. So 20 log of 0.891 shall be equals to negative 1 dB for omega between 0 and 10. So this will be your passband gain. So your passband frequency or the omega P shall be equals to 10. Okay. So from the first statement here, for the passband gain information, you are supposed to get your alpha P will be negative 1 dB, which is calculation of 20 log of 0.891. That will give us negative 1 dB. That will be alpha P, while your omega P will be 10. Whereas for the stop band region, it is given to be 0.0316. So this is in linear scale. So in dB, 20 log of 0.0316, we are supposed to get negative 30 dB. And based on this, it is given that the stop band frequency omega S shall be equals to 20. Okay, so from this information, from these questions, we have obtained the important parameters, the alpha P, the alpha S, omega P, and omega S. Okay. Right. So these are the questions. Number 1, calculate the filter order. And number 2, sketch the magnetic response of the filter. Number 3, determine the normalized transfer function. And number 4, determine the actual transfer function. Okay, this is a straightforward method. Yeah, but I'm going to show you clearly from this Butterworth response how to calculate these 4 important parameters. Yeah. Okay, so let's have a look at this calculation. Okay, so by using Okay, these are the equations that were extracted from the attachment. Yeah, H, J, omega, these are the equations. The alpha P is here. Okay, the alpha S is here. All right. This is alpha P, this is alpha S. This is a ratio between omega C and omega P and omega S. Yeah, and this is a ratio between omega S and omega C. Okay, and from this, we're going to calculate the N. N will be based on log 10 of this over 22 log of omega Sn. And since in these questions, we are requested to design a butterworth low-pass filter LPF, so your omega Sn that shall be used here will be omega S over omega P. Okay, so by substituting alpha S equals to 1 dB, sorry, alpha S equals to 30 dB, alpha P equals to 1 dB, omega S equals to 20 radian per second, omega P equals to 10 radian per second, we're supposed to get N equals to 5.9569, and this will give us 6. Okay, so in terms of the boat diagram, boat plot, the low pass filter should look like this. Okay, we have a pass band. Okay, yeah, this is your pass band gain. Yeah, pass band region, and this is your stop band region. So this is omega P. Okay, omega P and alpha P. So alpha P from this, okay, this is a linear scale, sorry. It's a linear scale. Supposedly in dB, this is supposed to be 0 dB, and this one should be equals to negative 1 dB, right? And for the alpha S, this one supposed to be equals to negative 30 dB, and omega S is 20 radian per second. Yeah. Okay. Hopefully it's clear about the boat diagram for this low pass filter. Okay, step number 2 is to determine the cutoff frequencies. Yeah, determine the cutoff frequencies. Right. So we are supposed to have two equations of omega C, as mentioned before, which is obtained from equation 6 and equation 7. You can refer to the notes, my notes. This is from equation 6, which is omega C is calculated based on the omega P and alpha P, whereas from equation 7, omega C cutoff will be based on the stop band region, which is omega S and the alpha S. So by calculating or by substituting those omega P, alpha P, omega S and alpha S together with N order, which is equals to 6, we are supposed to get two values of omega C now. The first one is 11.192 from the passband equations. Number 2 is 11.247 from the stop band equations. Okay, so we have two equations of cutoff frequencies, yeah? Okay, so these two cutoff frequencies, we need to choose either one of these. So in order for us to choose this omega C, these are the rule of thumb that I've mentioned in step 2 before. So step 2 states that we have to choose the cutoff frequency that will give calculated alpha P bigger than the spec of alpha P, calculated alpha S smaller than the spec of alpha S. So just to recall back the specification that we have from the previous questions, from these questions, we are given that the specification is alpha P, okay, alpha P is 0.891 in a linear scale or negative 1 dB, whereas the alpha S is negative 0.0316 or negative 30 dB in dB gain, in dB scale, yeah. Okay. So when we substitute these two cutoff frequencies in the equations 2 and equations 3, remember, I have to recall back, I have to get back to equations 2 and equations 3. Okay, these equations, yeah. So we have to substitute those omega C in these equations 2 and equations 3, 2 and 3, in order for us to calculate, to obtain the calculated alpha P and calculated alpha S, yeah. Okay, so let's proceed. Okay, so the first equation, the first omega C is 11.192. So in equations 2, we have alpha P is 0.0891. yeah, 0.0891, whereas for the alpha S, it is equals to 0.03069, in which the value is smaller than the specification, which is 0.0316, whereas for the alpha P, 0.0891 is bigger than the specifications, yeah? Yeah, because the spec is 0.0891. So in this calculation, the alpha P do have extra value up to 5 points here, yeah? Right. Whereas when we use omega C of 11.247, we can say that we can calculate that, yeah, you can prove on your own that the alpha S, calculated alpha S will be 0.032, which is bigger than the specification, which is 0.0316. Whereas for the alpha P, the value is 0.89966, which is bigger than the specification. So the problem now is that the alpha S, the calculated alpha S, by using this omega C value, is bigger than the specifications. So we cannot choose, or we cannot select this omega C of 11.247 because it does not follow the rule of thumb as stated here. So we have to choose omega C equals to 11.192 because it obeys the rule of thumb, because the calculated alpha P is bigger than the specification, while the calculated alpha S is smaller than the specifications. Okay, so for this, we're going to choose omega C equals to 11.192. I hope you are clear about this calculation, yeah, selection of omega C. If you have a problem with this selection of omega C, please contact me, ask me if you're not clear about this, yeah? Right. So now we're going to proceed with step number 3, in which for step number 3, we are going to determine the normalized transfer function H and S. Okay, so knowing that the n order is equals to 6, so the Butler's polynomial, the B and S, shall be equals to, based on this equation, so you're going to have A5, A4, A3, A2, and A1 here, and the normalized transfer function of H and S shall be equals to 1 over B and S. So we are supposed to get S power of 6 plus 3.864 S power of 5 plus 7.6464 S power 4 up to 3.864 of S plus 1. Yeah, so this is to obtain normalized transfer function when we consider the value of n equals to 6. Okay, and the final steps will be calculating the actual transfer function. So that will be need to use table F5, and knowing that we are referring to a low pass Butler's filter, so the transformation that need to be applied here is all the S value need to be transformed into S over omega C. Yeah, so replace all the S terms to S over omega C for a low pass Butler's filter, and from step 2 just now we have select omega C equals to 11.192. So in this calculation of the actual transfer function, all the S terms that we have from the previous normalized transfer function in step 3 shall be now substituted to be S over omega C as stated here. Okay, so that will be your actual transfer function from the given specification of your filter or low pass Butler's filter. Okay. All right. I'm going to stop here. In part 4 of lecture 19, we're going to proceed with these examples further. Yeah. Okay. Thank you.